Look up at the night sky and find the brightest star you can see. Chances are you're actually looking at Alpha Centauri, our nearest stellar neighbor, just 4.3 light-years away. In cosmic terms, that's practically next door. And yet, that tiny distance might as well be infinity. Because here's the heartbreaking truth. With our current technology, and possibly even with technologies we can barely imagine, we will likely never reach Alpha Centauri. Let's start with the basics. Alpha Centauri isn't actually one star. It's a system of 3 stars locked in a gravitational dance. Alpha Centauri A and B orbit each other like cosmic partners, while Proxima Centauri, a tiny red dwarf, circles the pair at a vast distance. Proxima is technically the closest to us at 4.24 light-years, which is why you'll sometimes hear it called our nearest stellar neighbor. Now, 4.24 light-years doesn't sound that far when you say it quickly, but let's break down what that really means. Light, the fastest thing in the universe, takes 4.24 years to make the journey. That's light traveling at 186,000 miles per second, fast enough to circle Earth 7.5 times in a single second. And even at that incomprehensible speed, it still takes over 4 years to reach our nearest neighbor. To put this in perspective, let's talk about Voyager 1, humanity's most distant spacecraft. Launched in 1977, Voyager 1 is now over 14 billion miles from Earth, sailing through interstellar space at about 38,000 miles per hour. That's faster than any human-made object has ever traveled. And at that speed, Voyager 1 would take about 73,000 years to reach Alpha Centauri if it were headed in that direction, which it's not. 73,000 years, that's longer than our entire recorded history. Longer than humans have been creating art. Nearly as long as our species has existed in its modern form. Entire civilizations could rise and fall dozens of times over before Voyager would arrive. But surely you might think we can go faster than Voyager. After all, that's 1970s technology. And you're right, we could go somewhat faster. The Parker Solar Probe, launched in 2018, will reach speeds of 430,000 miles per hour as it dives close to the Sun. But even at that blistering pace, a journey to Alpha Centauri would still take about 6,500 years. This is the fundamental problem we face. The universe is simply too big, and we are simply too slow. The distances between stars are so vast that they make even our most ambitious speeds look pathetic. It's like trying to swim across the Pacific Ocean, except the ocean is 1 trillion times wider, and you're 1 trillion times slower. Hey, if this is blowing your mind already, hit that subscribe button and like this video. Trust me, we're just getting started on this cosmic reality check, and I promise the journey will be worth it, even if we never actually make it to Alpha Centauri. But let's say we could somehow accelerate to 10% of light speed, a feat that would require revolutionary new propulsion technology. Even then, the journey would take 43 years. That's assuming we could instantly accelerate to that speed and instantly stop, which we can't. In reality, we'd need to spend years accelerating and years decelerating, pushing the journey time even longer. And here's where things get really complicated. As you approach significant fractions of light speed, Einstein's special relativity starts to rear its head. Time dilation means that while 43 years might pass on Earth, less time would pass for the travelers. That sounds like a benefit, but it creates a heartbreaking scenario. Everyone you know on Earth would age and die while you're traveling. You'd arrive at Alpha Centauri to find that nearly half a century has passed back home. But the problems don't stop there. At 10% of light speed, space itself becomes hostile. The cosmic void isn't empty. It contains about 1 hydrogen atom per cubic centimeter. That doesn't sound like much, but when you're traveling at 30,000 kilometers per second, those atoms hit your spacecraft like radiation bullets. The faster you go, the more deadly this becomes. At near-light speeds, this interstellar medium would create a radiation bath that would fry any human crew. Then there's the energy problem. To accelerate even a small spacecraft to 10% of light speed would require more energy than all of humanity currently produces in a year. And that's just for the acceleration. You'd need the same amount to slow down at your destination. The Breakthrough Starshot project, which aims to send tiny probes to Alpha Centauri, estimated they'd need a 100-gigawatt laser array. That's roughly the power output of 100 nuclear power plants, just to accelerate gram-sized spacecraft. And what about a human mission? The energy requirements scale up exponentially. A spacecraft large enough to support human life for decades would need a propulsion system beyond anything we can currently imagine. Fusion rockets, antimatter drives, Bussard ramjets, all of these remain firmly in the realm of theory, and even if we could build them, they might not be enough. Now let's talk about something that makes the challenge even more daunting. We don't even know if there's anything worth visiting when we get there. Proxima Centauri b, discovered in 2016 by the European Southern Observatory, is indeed in the habitable zone of its star. But habitable zone doesn't mean habitable, it just means liquid water could potentially exist on its surface. The reality is much more complicated and potentially heartbreaking. Proxima Centauri is what astronomers call a red dwarf star. These stars make up about 75% of all stars in our galaxy, so you'd think they'd be great places to look for life. But red dwarfs have a dark side that makes them particularly hostile to planets. They're prone to violent flares, sudden releases of energy that can be hundreds of times more powerful than anything our Sun produces. These flares bathe nearby planets in deadly radiation and can strip away their atmospheres entirely. When the European Space Agency's XMM Newton telescope observed Proxima Centauri in 2017, it detected a massive flare that increased the star's X-ray brightness by a factor of 68,000. For 11 seconds, this tiny star was pumping out more X-ray energy than our Sun produces in an entire day. Any planet in the habitable zone would have been scorched by radiation levels that would sterilize the surface. And this wasn't a rare event. Red dwarfs flare regularly throughout their incredibly long lifetimes. But let's say Proxima b has somehow maintained an atmosphere and even developed life. There's another cruel twist. The planet is almost certainly tidally locked to its star. This means one side permanently faces Proxima Centauri, baking in eternal day, while the other side faces away, frozen in eternal night. The temperature difference between these two hemispheres could be extreme, potentially hundreds of degrees. Any liquid water might exist only in a narrow twilight zone between the scorching day side and the frozen night side. Even if we could somehow reach Proxima b, we might find a world that's nothing like Earth. It could be a barren rock stripped of its atmosphere by stellar radiation. It could be a water world with crushing atmospheric pressure. It could be tidally locked with no day-night cycle, making it utterly alien to any Earth-based life form. We might travel for 40 years or more, only to find a world that's not only uninhabitable, but completely hostile to human life. And here's something that should give us pause. We're not even certain about the basic properties of this nearest exoplanet. We know it exists because we can detect the tiny gravitational tug it exerts on its star, but we don't know its mass precisely. We don't know if it has an atmosphere, and we certainly don't know if it has water or any conditions that might support life. We're essentially planning a decades-long journey to a world we know almost nothing about, based on the faintest of signals from across the void. The Alpha Centauri system presents other challenges that are rarely discussed. Alpha Centauri A and B, the two main stars, orbit each other in a complex dance that takes about 80 years to complete. Sometimes they're as close as 11 astronomical units apart, about the distance from our Sun to Saturn. Other times, they're as far as 36 astronomical units apart, roughly the distance to Pluto. This gravitational ballet affects everything in the system, making planetary orbits potentially unstable over long timescales. Any spacecraft approaching Alpha Centauri would have to navigate this three-body gravitational system, which is notoriously chaotic and difficult to predict. Small errors in trajectory could send a probe careening into one of the stars or flying off into interstellar space. And if we wanted to orbit or land on Proxima b, we'd need to slow down from interstellar speeds, a maneuver that would require carrying additional fuel or using some form of magnetic braking, adding complexity and mass to an already impossible mission. Let's consider the materials science challenges. A spacecraft designed for a 40-year journey needs to be built to last. Every component, electronics, life support systems, structural materials, needs to function flawlessly for decades in the harsh environment of space. We have no experience building anything that reliable. The International Space Station, humanity's most long-lived space habitat, has been in orbit for just over 20 years and requires constant maintenance and regular supply missions from Earth. The radiation environment of deep space slowly degrades electronic components, a process called total ionizing dose. Computer chips that work perfectly on Earth start to malfunction after years of cosmic ray bombardment. Solar panels lose efficiency as high-energy particles damage their crystalline structure. Materials become brittle as radiation breaks down their molecular bonds. A 40-year journey would push every component far beyond its design lifetime. Then there's the question of artificial intelligence and automation. Any interstellar mission would need to be largely autonomous given the communication delays with Earth. The spacecraft would need to make critical decisions on its own, diagnosing and repairing problems, navigating around obstacles, even deciding how to use its limited scientific instruments when it finally arrives. We're talking about creating an AI system more sophisticated than anything that currently exists, capable of operating independently for decades without human intervention. And let's not forget about the economics. Conservative estimates for an interstellar mission put the cost in the hundreds of billions of dollars, potentially more than the GDP of many countries. The Apollo program, which took us to the moon, cost about $150 billion in today's money and consumed about 4% of the entire US federal budget at its peak. An interstellar mission would be orders of magnitude more expensive and take orders of magnitude longer to complete. This brings us to a sobering political reality. No government has ever maintained funding for a project lasting longer than a few decades. Political priorities change, administrations change, and public interest waxes and wanes. The James Webb Space Telescope took nearly 30 years from concept to launch, and that was considered extraordinarily long for a space project. An interstellar mission would require unprecedented international cooperation and commitment spanning multiple generations of political leadership. But perhaps the most profound challenge is philosophical. Are we ready as a species to make the commitment that interstellar travel requires? It would mean dedicating enormous resources to a project that wouldn't pay off for decades or centuries. It would mean making decisions on behalf of future generations, possibly condemning them to life aboard a spacecraft or on an alien world they didn't choose. It would mean accepting that the crew or their descendants might never return to Earth. There's also the question of what happens to human evolution during such a journey. Isolated populations evolve differently, and a small group of humans isolated aboard a spacecraft for generations might become genetically distinct from Earth's population. They might develop different physical characteristics adapted to space life, different cultural practices, even different languages. The humans who arrive at Alpha Centauri might be as different from us as we are from our ancestors of 40,000 years ago. So maybe you're thinking, okay, conventional rockets won't work, but what about all those science fiction technologies? Fusion drives, antimatter engines, solar sails, generation ships? Let's examine these supposed solutions and see why each one runs headfirst into the laws of physics, like a bug hitting a windshield at light speed. Fusion propulsion sounds promising at first. After all, fusion powers the stars themselves. Surely we can harness that energy for space travel. The concept is straightforward. Fuse hydrogen nuclei together, release enormous amounts of energy, and use that to propel your spacecraft. Fusion reactions produce about 10 times more energy per unit mass than the best chemical rockets, which sounds like a game changer until you run the numbers. Even with perfect fusion efficiency, something we haven't achieved in 70 years of trying, a fusion rocket would still need a fuel mass several times the mass of the payload to reach Alpha Centauri in reasonable time. And that's assuming 100% efficiency, which violates thermodynamics. Real fusion rockets would be much less efficient, requiring even more fuel. The ITER project, humanity's most ambitious fusion experiment, has consumed over $20 billion and taken 30 years just to build a reactor that might achieve fusion for a few minutes. Scaling that up to a reliable spacecraft engine is a challenge of staggering proportions. But let's say we solve fusion propulsion completely. There's still the problem of fuel. The best fusion reaction for spacecraft uses deuterium and helium-3, but helium-3 is incredibly rare on Earth. Most proposals involve mining it from the Moon's surface, where it's been deposited by billions of years of solar wind. But lunar mining is its own technological challenge that doesn't exist yet. We'd need to establish industrial infrastructure on the Moon, extract and process helium-3, and transport it back to Earth, all before we could even think about building our interstellar spacecraft. Antimatter propulsion represents the theoretical upper limit of chemical propulsion efficiency. When matter and antimatter annihilate, they convert 100% of their mass into energy according to Einstein's E equals mc squared. This is the most energetic reaction possible in the universe, making antimatter the ultimate rocket fuel. The problem? We can barely make antimatter at all, let alone store it safely. The Large Hadron Collider at CERN, the most powerful particle accelerator on Earth, produces about 10 billion antiprotons per minute. That sounds impressive until you realize that 10 billion antiprotons weigh about 1.5 femtograms. That's 0.00000000000000015 grams. At current production rates, it would take about 100 billion years to produce a single gram of antimatter. Even if we improved our production efficiency by a factor of 1,000,000, we'd still need 100,000 years to produce enough antimatter for an interstellar mission. And that's just production. Storing antimatter is another nightmare entirely. Antimatter can't touch any normal matter without annihilating instantly, so it must be contained using magnetic fields in perfect vacuum chambers. The most advanced antimatter traps can hold a few thousand antiprotons for a few hours before they escape and annihilate. Storing the kilograms of antimatter needed for an interstellar mission would require technology so advanced it might as well be magic. Solar sails offer a different approach, using the pressure of light itself for propulsion. The concept is elegant. Deploy enormous ultra-thin sails that catch photons from the sun or powerful lasers, gradually accelerating to high speeds without carrying any fuel. The Japanese Icaros mission proved that solar sails work in practice, and the Planetary Society's light sail missions have demonstrated controlled sailing in Earth orbit. But scaling this up to interstellar missions reveals crushing limitations. To accelerate a meaningful payload to even 10% of light speed using solar sails would require sails measured in square kilometers. Imagine a mirror the size of a small city, made from material thinner than a soap bubble, that must remain perfectly deployed and controlled across decades of acceleration. The Breakthrough Starshot project proposes sails just 4 meters across for gram-sized payloads, and even that faces enormous technical challenges. The laser system needed for Breakthrough Starshot would be a marvel of engineering, a phased array of thousands of individual lasers, each precisely controlled to create a coherent beam focused on a target just meters across. The total power requirement is about 100 gigawatts, roughly equivalent to the entire electrical output of the United Kingdom, and that's just for accelerating tiny chips. A human mission would require laser arrays measured in hundreds of square kilometers, consuming more power than all of human civilization currently produces. But here's the cruel irony of solar sails: the faster they go, the less effective they become. As you approach significant fractions of light speed, the relative velocity between your sail and the laser light decreases due to relativistic effects. The acceleration drops off dramatically just when you need it most. And unlike rockets, you can't just shut off the engine when you reach your target. There's no way to slow down. You zip past Alpha Centauri in a matter of hours after decades of acceleration, with barely enough time to take a few hurried measurements. Generation ships represent perhaps the most ambitious solution. Build spacecraft so large and so well equipped that entire civilizations can live aboard them during the centuries-long journey to Alpha Centauri. The concept is compelling in its boldness. If we can't make the trip faster, we'll just bring Earth with us. But generation ships face challenges that go far beyond engineering into the realm of sociology, psychology, and ethics. Consider the scale required. A self-sustaining generation ship would need to support thousands of people through multiple generations. It would need closed-loop life support systems that never fail, manufacturing capabilities to build and repair everything from computer chips to medical equipment, genetic diversity to prevent inbreeding, and somehow maintain the technological and cultural knowledge needed to complete the mission. We've never built a closed ecological system that works reliably for more than a few years, let alone centuries. The Stanford Torus, designed in 1976 as a space settlement concept, would house 10,000 people in a rotating cylinder 1.8 kilometers in diameter. Building such a structure would require more steel than humanity has produced in the last century. Accelerating it to even a fraction of light speed would require energy equivalent to all the electricity generated on Earth for several years. And that's just one example. Most generation ship designs are even more massive. The psychological challenges might be insurmountable. Imagine being born aboard a spacecraft knowing you'll live your entire life in an artificial environment, never seeing a natural sky, never feeling wind or rain, never having the choice to go anywhere else. The sociological stresses could tear apart the mission before it's halfway complete. What happens if different factions develop different ideas about the mission's goals? What if people decide they don't want to go to Alpha Centauri after all? There's no turning back once you're decades into the journey. And then there are the biological challenges of multi-generational space travel. We don't fully understand how human reproduction and development would be affected by decades of life in space. Would children born in artificial gravity develop normally? How would the absence of Earth's magnetic field affect developing brains? Would the limited genetic diversity of the initial population lead to harmful inbreeding over time? Even more exotic propulsion concepts fail when subjected to careful analysis. Bussard ramjets, which would scoop up interstellar hydrogen for fuel, were once considered promising for interstellar travel. But detailed studies showed that the drag from the magnetic field needed to collect the hydrogen would actually slow the spacecraft down more than the collected fuel would speed it up. Nuclear pulse propulsion, like the old Project Orion concept, could potentially reach a few % of light speed, but would require thousands of nuclear explosions and create a radiation hazard extending across the entire solar system. Warp drive and other faster-than-light concepts remain firmly in the realm of speculation. The Alcubierre drive, proposed in 1994, could theoretically allow faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. But it would require exotic matter with negative energy density, something that may not exist in nature and certainly doesn't exist in any laboratory. The energy requirements are also staggering. Some calculations suggest it would take more energy than exists in the observable universe to create a warp bubble just a few meters across. Let's dig deeper into something that makes interstellar travel even more challenging than most people realize. The space between stars isn't empty. When we look up at the night sky, the darkness between stars seems like a perfect void, but that's an illusion created by the limitations of our eyes. Interstellar space is filled with gas, dust, magnetic fields, and high-energy particles that turn any high-speed journey into a gauntlet of destruction. The local bubble, the region of space surrounding our solar system, was carved out by ancient supernovae that blew away most of the gas and dust about 10 million years ago. This makes our neighborhood unusually empty, only about 0.1 atoms per cubic centimeter. That might sound like nothing, but remember, we're talking about traveling at 10 or 20% of light speed. At those velocities, even individual atoms become deadly projectiles. Imagine driving your car at 60 miles per hour through a swarm of mosquitoes. Now imagine those mosquitoes are hydrogen atoms, and you're traveling at 60 million miles per hour. Each impact delivers energy equivalent to a high-speed particle accelerator. The spacecraft would need massive shielding just to survive the constant bombardment, adding weight that makes the propulsion challenge even worse. NASA's New Horizons mission, traveling at a mere 39,000 miles per hour, still had to be designed to survive impacts from dust grains smaller than rice grains. But hydrogen atoms are just the beginning. Interstellar space also contains larger dust grains, particles of carbon, silicon, and iron that formed in the atmospheres of dying stars billions of years ago. These grains are typically smaller than the particles in cigarette smoke, but at interstellar velocities, even a grain the size of a bacterium would hit with the force of a hand grenade. The Giotto spacecraft, which flew past Halley's Comet in 1986 at a relatively modest 43 miles per second, was peppered with over 12,000 dust impacts in just a few hours. Then there are the cosmic rays, high-energy particles accelerated by supernovae, pulsars, and other violent cosmic events. These particles can penetrate meters of solid shielding and wreak havoc on both electronics and biological systems. The most energetic cosmic rays carry more energy than a major league fastball, concentrated into a single atomic nucleus. Over the decades of an interstellar journey, the cumulative radiation dose would be lethal many times over, even with the best shielding we can imagine. The magnetic fields threading through interstellar space add another layer of complexity. These fields, generated by the motion of charged particles in space, can deflect and trap cosmic rays, creating regions of intense radiation. They can also interact with any magnetic shielding system on a spacecraft, potentially disrupting navigation and communication systems. The Voyager probes have detected complex magnetic structures throughout the heliosphere, the bubble of charged particles surrounding our solar system, and beyond. Recent discoveries have revealed that interstellar space is even more hostile than we previously thought. The Voyager missions, now traveling through true interstellar space, have detected intense plasma waves and unexpected magnetic phenomena. In 2021, Voyager 1 detected a persistent hum of plasma oscillations, the sound of interstellar space itself vibrating like a cosmic violin string. These discoveries suggest that interstellar space is far more dynamic and potentially hazardous than the empty void we once imagined. But perhaps the most sobering recent discovery concerns the local interstellar cloud, a wisp of gas and dust that our solar system is currently passing through. Analysis of data from the Interstellar Boundary Explorer satellite has revealed that this cloud contains significantly more heavy elements than expected, including iron and oxygen atoms that could pose serious hazards to high-speed spacecraft. We're essentially traveling through the remnants of ancient stars, the ashes of cosmic explosions that occurred millions of years ago. The heliosphere itself, the protective bubble created by our sun's solar wind, provides some shielding from interstellar hazards, but only out to about 120 astronomical units from the Sun. That's roughly 3 times farther than Pluto's orbit, but still less than 1,000th of the distance to Alpha Centauri. Once a spacecraft leaves the heliosphere, it's completely exposed to the full fury of interstellar space. And here's something that keeps me awake at night, thinking about it. We don't fully understand the structure of nearby interstellar space. The local bubble is part of a larger network of cavities and dense clouds that astronomers call the local interstellar medium. Recent three-dimensional mapping using data from the European Space Agency's Gaia satellite has revealed that this region is far more complex than we realized, with dense molecular clouds, stellar associations, and supernova remnants creating a constantly changing environment. An interstellar spacecraft might encounter regions where the density of gas and dust is hundreds of times higher than in the local bubble. Imagine flying at 20% of light speed into a molecular cloud. The spacecraft would be vaporized in seconds. These clouds can extend for dozens of light years, and their boundaries aren't clearly marked with warning signs. A spacecraft would need sophisticated sensors to detect such hazards years in advance, and powerful propulsion systems to change course, adding more complexity and mass to an already impossible design. Temperature presents another challenge rarely discussed. Interstellar space is cold, about 2.7 Kelvin, just a few degrees above absolute zero. That's the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang itself. Any spacecraft would need heating systems capable of operating for decades to prevent critical components from freezing. But heating systems require power, and power generation in the depths of space, far from any star, is a significant challenge. Solar panels become useless beyond a few astronomical units from the Sun, which is why deep space missions like Voyager and New Horizons use radioisotope thermoelectric generators, essentially nuclear batteries that convert the heat from radioactive decay into electricity. But even these systems gradually lose power over time as their radioactive fuel decays. A 40-year mission would require either massive amounts of radioactive fuel or some form of nuclear reactor capable of operating autonomously for decades. The communications challenge becomes truly mind-boggling when you consider the full journey. NASA's Deep Space Network, consisting of giant radio dishes scattered around Earth, can barely maintain contact with Voyager 1 at its current distance of over 14 billion miles. The signal is so weak that it arrives with less power than a snowflake hitting the ground. An interstellar spacecraft would quickly become impossible to contact using conventional radio technology. Laser communication offers higher data rates and more focused beams, but it requires incredibly precise pointing. A spacecraft halfway to Alpha Centauri would need to aim its laser transmitter to within a few billionths of a degree to hit Earth, like threading a needle from the distance of the Moon. Any slight vibration, thermal expansion, or mechanical wear could break the communication link permanently, leaving the spacecraft to continue its journey in complete isolation from human contact. The psychological impact of this isolation cannot be overstated. Every previous human space mission has maintained some form of real-time or near real-time communication with Earth. Even astronauts on the Moon could talk to mission control with only a few seconds of delay. An interstellar crew would face years of complete isolation, knowing that any message they send would take years to reach Earth and years more for a response to return. They would truly be on their own in a way that no human has ever experienced. And then there's the question of what we find when we get there. Our knowledge of the Alpha Centauri system is still remarkably limited. We know that Proxima b exists, but we don't know its mass, its atmospheric composition, its magnetic field strength, or even whether it has any atmosphere at all. The James Webb Space Telescope and other next-generation instruments may answer some of these questions in the coming years, but by the time we launch an interstellar mission, we'll still be making the journey based on incomplete information. Recent studies of red dwarf stars like Proxima Centauri have revealed that they're even more hostile to planets than we initially thought. The Transiting Exoplanet Survey satellite has observed numerous red dwarfs undergoing superflares, explosive events that release more energy in a few minutes than our Sun produces in an entire year. These flares can strip away planetary atmospheres, sterilize surfaces, and create radiation environments that would be lethal to any Earth-based life form. Now let's talk about something that doesn't get nearly enough attention when people fantasize about interstellar travel. The human body simply wasn't designed for this journey. Evolution spent millions of years adapting us to Earth's specific environment, its gravity, its atmosphere, its magnetic field, its 24-hour day-night cycle. Take us away from Earth for decades, and our bodies begin to rebel in ways that are both predictable and terrifying. We've learned about some of these effects from astronauts on the International Space Station, but those missions last only 6 months to a year. Even in that short time, astronauts lose significant bone density, muscle mass, and cardiovascular fitness. Their eyes change shape, affecting vision. Their immune systems become compromised. Their circadian rhythms get disrupted. And remember, ISS astronauts are still within Earth's protective magnetosphere, shielded from the worst cosmic radiation. An interstellar crew would face these challenges magnified by decades of exposure. Bone loss in space occurs at a rate of about 1 to 2% per month. On a 40-year journey to Alpha Centauri, even with the best exercise regimens and medical countermeasures, crew members could lose 50 to 80% of their bone mass. Their skeletons would become so fragile that the stress of arriving at destination, possibly including landing on a planet with gravity, could cause catastrophic fractures. We're talking about people whose bones would be more fragile than those of 90-year-old osteoporosis patients. The muscle atrophy is equally devastating. In microgravity, muscles don't need to work against their own weight, so they begin to waste away. The heart, which is essentially a muscle, becomes deconditioned and struggles to pump blood effectively. After decades in space, crew members might lack the physical strength to operate their spacecraft or perform the complex tasks needed upon arrival. The irony is cruel. By the time you reach your destination, you might be too weak to explore it, but the psychological challenges might be even worse than the physical ones. Consider the confinement. Even the largest proposed generation ships would be smaller than a typical small town, and there's no possibility of leaving, ever. Imagine being locked in the same building with the same people for 40 years, knowing that everyone you've ever known on Earth is aging and dying while you crawl through the void. The psychological term for this is environmental psychology syndrome, and it includes depression, anxiety, cognitive decline, and potential psychotic breaks. We've seen hints of these problems even on short-duration missions. Soviet cosmonaut Valentin Lebedev wrote extensively about the psychological toll of spending 211 days aboard the Salyut 7 space station in 1982. He described periods of deep depression, interpersonal conflicts with his crewmate, and an overwhelming sense of isolation. And that was just 7 months, with regular communication with Earth and the knowledge that rescue was possible if something went catastrophically wrong. The sensory deprivation of interstellar space would be unlike anything humans have ever experienced. Outside the spacecraft windows, absolute darkness punctuated only by stars that appear as fixed points of light. No weather, no seasons, no sunrise or sunset, no natural sounds except the mechanical hum of life support systems. The human brain, evolved to process complex natural environments, might begin to malfunction after years of such monotony. Sleep becomes a challenge when there's no natural day-night cycle. Even with artificial lighting systems, many astronauts struggle with insomnia and circadian rhythm disorders. Over the course of decades, chronic sleep disruption could lead to cognitive decline, memory problems, and increased risk of psychiatric disorders. The crew would need to maintain alertness and decision-making ability for the entire journey, but their brains would be slowly degrading from environmental factors beyond their control. Social dynamics in such a confined environment could become explosive. Earth-based studies of isolated groups, Antarctic research stations, submarine crews, Mars simulation facilities consistently show that interpersonal conflicts increase over time. Small annoyances become major disputes. Leadership structures break down, cliques form and turn against each other. Now imagine these dynamics playing out over decades with no possibility of escape or outside intervention. The genetic implications of a small, isolated population are also sobering. To maintain genetic diversity and prevent inbreeding, an interstellar colony would need a founding population of at least several hundred people, and even then, careful genetic management would be required across generations. Computer models suggest that populations smaller than a few thousand individuals risk genetic bottlenecks that could lead to reduced fertility, increased susceptibility to disease, and potential extinction of the colony. But let's step back from the human factors and consider the engineering nightmare of building something that absolutely must work perfectly for 40 years or more. We have no experience creating technology that reliable. The longest operating spacecraft in history are the Voyager probes, launched in 1977, and they're already experiencing system failures after just over 40 years. Voyager 2's plasma science instrument failed in 1987, its fuel pressure transducer failed in 1990. Multiple other instruments have failed over the decades, and mission controllers have had to constantly improvise workarounds and shut down non-essential systems to conserve power. And the Voyagers are relatively simple spacecraft with minimal moving parts and no life support systems. An interstellar mission carrying humans would require vastly more complex systems: life support, food production, waste recycling, medical equipment, manufacturing capabilities, and all the computer systems needed to control everything autonomously. Every single component would need to function flawlessly for decades because there's no possibility of repair or replacement from Earth. Consider just the life support system. On the International Space Station, critical components are routinely replaced and repaired using supplies delivered by cargo spacecraft. Filters get clogged, pumps wear out, computer modules fail, and seals begin to leak. An interstellar spacecraft would need redundant backups for every critical system, but even redundancy has limits. If your primary oxygen generation system fails after 20 years and your backup fails after 30 years, you still have 10 years left in your journey breathing whatever oxygen you have stored, assuming you've managed to store 40 years' worth, which presents its own engineering challenges. The computer systems required for such a mission stretch the limits of reliability engineering. The spacecraft would need to operate autonomously for decades, making critical decisions about navigation, life support, and mission operations without any input from Earth. Modern computers are incredibly powerful, but they're also incredibly complex and prone to failure. Software bugs, hardware degradation, cosmic ray-induced errors, and component aging all conspire to make long-term computer reliability a nearly impossible challenge. NASA's experience with long-duration missions provides sobering lessons. The Opportunity rover on Mars was designed for a 90-day mission, but operated for nearly 15 years, an incredible success story. But even Opportunity experienced multiple system failures over its extended mission: stuck wheels, failed heaters, degraded solar panels, and memory problems. Mission controllers had to constantly adapt to these failures, uploading new software and developing creative workarounds. An interstellar spacecraft wouldn't have that luxury of constant human oversight and intervention. The materials science challenges are equally daunting. Decades of cosmic radiation gradually break down molecular bonds in metals, plastics, and composites. Materials that seem perfectly stable on Earth become brittle and unreliable after years of high-energy particle bombardment. Seals that prevent air from leaking into space begin to degrade. Metal components develop microscopic cracks that grow over time. Electronic circuits accumulate damage that eventually leads to failure. And then there's the problem of consumables. Every spacecraft needs lubricants for moving parts, chemicals for life support systems, spare electronic components for repairs, and medical supplies for the crew. Calculating 40 years' worth of supplies is a nightmare of logistics and probability. How many spare computer processors do you need? How much medical equipment? What if someone develops appendicitis 20 years into the journey? What if the water recycling system starts producing contaminants that require additional filtration chemicals you didn't anticipate? The economic reality of interstellar missions is perhaps the most crushing obstacle of all. Conservative estimates put the cost of a human mission to Alpha Centauri at several $trillion, more than the GDP of most countries. The Apollo program, which took us to the Moon, consumed about 4% of the entire United States federal budget at its peak and cost roughly $150 billion in today's money. An interstellar mission would be orders of magnitude more expensive and take orders of magnitude longer to complete. No government in history has maintained funding for a project lasting multiple decades without interruption. Political priorities change, economies fluctuate, and public interest waxes and wanes. The James Webb Space Telescope took nearly 30 years from concept to launch and faced numerous budget cuts and cancellations along the way. The International Space Station has been under constant political pressure throughout its existence, with funding often uncertain from year to year. An interstellar mission would require sustained political and financial commitment spanning multiple generations, something that has never been achieved for any project in human history. The international cooperation required would be unprecedented. No single nation has the resources to mount an interstellar mission alone, which means bringing together countries with different political systems, economic priorities, and technological capabilities. The history of international space cooperation, while generally positive, is filled with delays, cost overruns, and political tensions. The International Space Station partnership has worked reasonably well, but even that has faced challenges from changing geopolitical relationships and differing national priorities. There's another crushing reality we need to face. By the time we develop the technology to actually attempt an interstellar mission, the mission itself might be obsolete before it even launches. This is called the weight calculation, and it's one of the most depressing paradoxes in all of space exploration. The logic is simple but brutal. If technology is improving rapidly, it might make sense to wait for better technology rather than launching with current capabilities. Consider this scenario. We somehow develop the technology to send a spacecraft to Alpha Centauri in 40 years using 21st century propulsion. But while that spacecraft is crawling through space, technology continues to advance. 50 years from now, we might have propulsion systems that could make the same journey in 20 years, 100 years from now, maybe 10 years. The cruel mathematics suggests that any early interstellar mission might be overtaken by faster missions launched decades later using superior technology. This isn't just theoretical speculation. We've seen this exact phenomenon play out in planetary exploration. The Voyager probes, launched in 1977, took 9 years to reach Jupiter and 12 years to reach Neptune. But Juno, launched in 2011 with better technology, reached Jupiter in just 5 years. New Horizons, launched in 2006, reached Pluto in 9 years, a journey that would have taken Voyager much longer. Each successive generation of spacecraft is faster, more capable, and more efficient than the last. The weight calculation becomes even more depressing when you consider the exponential pace of technological development. Computer processing power roughly doubles every 18 months, according to Moore's law. Materials science is advancing rapidly, with new metamaterials, carbon nanotubes, and graphene-based technologies emerging regularly. Propulsion research is exploring concepts that were pure science fiction just decades ago: fusion rockets, antimatter catalyzed propulsion, even theoretical breakthrough physics like the Alcubierre warp drive. If we launched an interstellar mission today using the best technology available, it would almost certainly be obsolete before reaching its destination. But if we wait for better technology, there's always the possibility of even better technology being developed while we wait. It's a cosmic catch-22 that could postpone interstellar travel indefinitely. Some researchers have calculated that, given reasonable assumptions about technological progress, the optimal time to launch an interstellar mission is never. There's always a mathematically compelling argument to wait just a little longer. But let's assume we somehow overcome the weight calculation and decide to launch anyway. There's still the terrifying problem of navigation across interstellar distances. When Apollo astronauts traveled to the Moon, they had constant communication with mission control and could make course corrections throughout their journey. An interstellar spacecraft would be essentially flying blind for most of its journey, relying on navigation systems that must work perfectly for decades without any guidance from Earth. The precision required is staggering. Alpha Centauri isn't sitting still. It's moving through space at about 22 kilometers per second relative to our Sun. Over a 40-year journey, it will move roughly 27 billion kilometers from its current position. That's about the distance from the Sun to Neptune. The spacecraft must be aimed not at where Alpha Centauri is now, but at where it will be 4 decades from now. Any error in this calculation, no matter how small, could send the spacecraft careening past the target system and into the void beyond. But the navigation challenge goes deeper than just hitting a moving target. Space itself isn't empty. It's filled with gravitational influences that can gradually alter a spacecraft's trajectory. The gravitational fields of Jupiter, Saturn, and other massive objects in our solar system continue to influence spacecraft long after they've left the inner solar system. Even tiny asteroids can exert measurable gravitational effects over the course of decades, and once a spacecraft leaves our solar system entirely, it enters the gravitational influence of nearby stars, brown dwarfs, and other massive objects we may not even know about. Recent discoveries have revealed that our stellar neighborhood is more crowded and dynamic than we previously thought. The European Space Agency's Gaia satellite has identified numerous stealth objects, brown dwarfs, white dwarfs, and other dark objects that don't emit much light but do exert gravitational influence. Some of these objects are moving at high speeds through interstellar space, their gravitational fields creating a constantly changing navigation environment that would be impossible to predict decades in advance. Then there's the problem of stellar motion itself. Our Sun, along with the Alpha Centauri system and all nearby stars, is orbiting around the center of the Milky Way galaxy at about 230 kilometers per second. This galactic rotation isn't perfectly uniform. Different regions of the galaxy rotate at slightly different speeds, creating a phenomenon called differential rotation. Over the course of a 40-year interstellar journey, these subtle differences in galactic motion could accumulate into significant navigation errors. The communication delays make the navigation problem even worse. By the time a spacecraft is halfway to Alpha Centauri, radio signals take over 2 years to travel between the spacecraft and Earth. If mission controllers detect a navigation error, it takes 2 years for the correction signal to reach the spacecraft, and by then the spacecraft has traveled billions of additional kilometers in the wrong direction. For practical purposes, the spacecraft must navigate autonomously, making its own decisions about course corrections based on onboard sensors and computer systems. And what happens if something goes wrong? There's no possibility of rescue or repair. If a critical navigation sensor fails, if the computer system experiences a catastrophic error, if the spacecraft gets knocked off course by an unexpected collision with interstellar debris, the mission is simply over. The crew would face the horrifying reality of being lost in interstellar space, billions of kilometers from any hope of rescue, with no choice but to wait out their remaining life support while drifting through the cosmic void. The psychological impact of this level of risk and isolation goes beyond anything humans have ever experienced. Every previous exploration mission in human history, from Magellan's circumnavigation to moon landings to Arctic expeditions, has maintained at least the theoretical possibility of rescue or return. An interstellar crew would be truly, utterly alone in a way that no human has ever been. The knowledge that they are farther from help than anyone in human history, traveling through a hostile environment where the slightest mistake means death, would create psychological pressures we can't fully anticipate. Recent studies of extreme isolation, Antarctic research stations, submarine patrols, Mars simulation experiments have revealed that humans don't adapt well to prolonged separation from Earth's natural environment. Researchers have documented something called Earth out of view phenomenon, where astronauts who can no longer see Earth experience profound psychological distress. An interstellar crew would experience this phenomenon magnified by decades of separation from everything familiar and comforting. But perhaps the most sobering consideration is this: we might be solving the wrong problem entirely. The assumption underlying all interstellar mission planning is that we need to send biological humans to Alpha Centauri. But by the time we develop the technology for such missions, advances in artificial intelligence, robotics, and possibly even consciousness uploading might offer alternatives that are faster, cheaper, and more reliable. Consider sending advanced artificial intelligence instead of humans. An AI probe wouldn't need life support, wouldn't suffer bone loss or psychological problems, and could potentially operate for centuries without degradation. It could be built smaller and lighter, making the propulsion challenge more manageable. It could make decisions at computer speeds rather than human speeds, potentially allowing for more sophisticated navigation and scientific observations. And if something goes wrong, we could potentially upload new software to fix problems, something that's impossible with biological systems. The rapid advancement of AI technology makes this possibility increasingly plausible. Machine learning systems are already surpassing human performance in numerous specialized tasks. By the time we're ready to launch interstellar missions, AI systems might be sophisticated enough to conduct scientific research, make complex decisions, and even engage in meaningful communication with any life forms they encounter. They could serve as our ambassadors to the stars, carrying human knowledge and perspectives without requiring the massive infrastructure needed to keep biological humans alive. Even more speculative is the possibility of uploading human consciousness to digital form. If neuroscience advances to the point where we can map and simulate human brains in sufficient detail, we might be able to send human minds to Alpha Centauri without sending human bodies. Digital consciousness wouldn't need air, water, food, or radiation shielding. It could potentially exist for indefinite periods, experiencing subjective time at variable speeds depending on computational resources. The uploaded explorers could slow down their subjective experience during the long journey and speed it up upon arrival to maximize their exploration time. These possibilities might sound like science fiction, but they're based on technologies that are advancing rapidly. Brain-computer interfaces are becoming more sophisticated every year. Artificial neural networks are growing in complexity and capability. Quantum computers might eventually provide the computational power needed to simulate consciousness in real time. While we're still far from achieving consciousness uploading, the timeline for developing this technology might be comparable to the timeline for developing reliable interstellar propulsion. The resources required for an interstellar mission are so enormous that we should seriously consider whether they might be better invested in other approaches to the same goals. If our objective is to extend human presence beyond Earth, we might achieve more by establishing permanent settlements throughout our own solar system. If our goal is to search for life, we might learn more by studying the potentially habitable moons of Jupiter and Saturn. If we want to expand human knowledge and capability, we might make greater progress by investing in fundamental research in physics, biology, and computer science. Mars, for all its challenges, is vastly more accessible than Alpha Centauri. The journey takes months rather than decades, communication delays are measured in minutes rather than years, and rescue missions are at least theoretically possible. Establishing a self-sustaining colony on Mars would require solving many of the same technical challenges as an interstellar mission: closed-loop life support, radiation shielding, psychological adaptation to isolation, but with significantly lower risks and costs. The moons of the outer solar system might offer even better opportunities for finding life. Europa, Enceladus, and Titan all show evidence of subsurface oceans that might harbor microbial life. These worlds are exotic and challenging to reach, but they're still within our solar system, making robotic exploration feasible with current or near-future technology. Discovering life in these local oceans might teach us more about the possibilities for life around other stars than actually visiting those stars would. Let's talk about something that puts our Alpha Centauri dreams into an even more sobering perspective: the sheer scale of what we're attempting. When we look up at Alpha Centauri with our naked eyes, it appears as a single bright star, seemingly close and accessible. But the reality is that we're trying to bridge a gap so vast that it challenges our ability to comprehend distance itself. To truly understand why Alpha Centauri might remain forever beyond our reach, we need to grasp just how big space really is. If we scaled down the universe to make it more comprehensible, the distances involved would still be staggering. Imagine shrinking the sun to the size of a basketball. On this scale, Earth would be a peppercorn orbiting about 26 yards away. Jupiter would be a small marble at about 140 yards. Pluto, at the edge of our solar system, would be another peppercorn nearly a mile away. And Alpha Centauri, it would be another basketball sitting 7,000 miles away, roughly the distance from New York to Paris. Think about that for a moment. If our entire solar system from the Sun to Pluto fits within a circle 1 mile across, then the nearest star is 7,000 miles away. That's the cosmic neighborhood we're trying to navigate. Every science fiction movie that shows spacecraft casually hopping between star systems is depicting something as fantastical as magic carpets or flying unicorns. The universe simply doesn't work that way. This scale problem becomes even more overwhelming when you consider that Alpha Centauri isn't just far away, it's moving. At 7,000 miles away on our basketball scale, Alpha Centauri is traveling sideways at about 20 miles per hour. Over the course of a 40-year journey, it would move roughly 7,000 miles from its starting position, a distance equal to the entire gap we're trying to cross. We're not just throwing a basketball 7,000 miles, we're trying to hit a basketball that's moving at 20 miles per hour, and we can't adjust our throw once we've released it. The energy scales involved are equally mind-boggling. Every chemical rocket ever built works by essentially having an explosion in a contained chamber and directing the blast out the back. It's a brute force approach that requires carrying enormous amounts of fuel. To reach Alpha Centauri in a reasonable time, you need to achieve velocities that chemical rockets simply cannot provide, no matter how much fuel you carry. It's like trying to jump to the moon. No amount of leg muscle will ever be sufficient because the physics fundamentally don't work. Even nuclear energy, the most powerful force we've learned to harness, falls short of what's needed for practical interstellar travel. The energy density of nuclear reactions is about 10 million times greater than chemical reactions, which sounds promising until you run the numbers. To accelerate even a small spacecraft to 10% of light speed using perfect fusion propulsion would require more energy than all of human civilization produces in an entire year. And that's just for the acceleration. You need the same amount again to slow down at your destination. The fundamental problem is that energy requirements increase with the square of velocity. Going twice as fast requires 4 times as much energy. Going 10 times as fast requires 100 times as much energy. This quadratic relationship creates a brutal barrier to high-speed travel. Chemical rockets can achieve maybe 1,000th of the speed of light. To reach even 10% of light speed, still 43 years to Alpha Centauri, requires 1 million times more energy than chemical propulsion can provide. But let's step back from the technical challenges and consider something even more fundamental, the possibility that interstellar travel might be physically impossible for biological life forms. Evolution optimized us for survival on Earth's surface, not for decades-long journeys through the radiation-soaked vacuum of space. Every system in our bodies, from our cardiovascular system to our immune system to our psychological makeup, depends on Earth's specific environment. Recent research on the International Space Station has revealed that space travel affects the human body in ways we're still discovering. Astronaut Scott Kelly spent nearly a year in space as part of NASA's twin study, and researchers found significant changes in his gene expression, immune function, and even the structure of his chromosomes. Some of these changes persisted for months after his return to Earth. Now imagine these effects accumulating over decades rather than months. The twin study revealed that prolonged spaceflight affects telomeres, the protective caps on chromosomes that shorten as we age. Some of Kelly's telomeres actually lengthened in space, which initially seemed positive, but they shortened dramatically upon his return to Earth, potentially accelerating aging. His cognitive performance declined during the mission and took months to recover. His gut bacteria changed significantly, affecting digestion and immune function. These are just the effects we can measure. There may be subtle changes we haven't even identified yet. Now multiply these effects by 40 years instead of 1 year. Add the constant bombardment of cosmic radiation far from Earth's protective magnetosphere. Include the psychological stress of complete isolation from Earth, and the knowledge that everyone you've ever known is aging and dying while you crawl through the void. Factor in the inevitable equipment failures, the gradual degradation of your spacecraft, and the constant threat of catastrophic accidents with no possibility of rescue. The picture that emerges is not one of heroic exploration, but of a journey that might well be a death sentence. The radiation exposure alone could be mission-killing. Beyond Earth's magnetosphere, cosmic rays constantly bombard spacecraft with high-energy particles that can damage DNA and increase cancer risk. The Apollo astronauts who spent only a few days in deep space reported seeing flashes of light when cosmic rays hit their retinas. Over the course of decades, this radiation exposure would accumulate to levels that are almost certainly lethal. Current radiation shielding technology is far too heavy for practical spacecraft, and even the most advanced concepts wouldn't provide complete protection. But perhaps the most sobering realization is that we might be approaching this problem from entirely the wrong direction. The assumption that humans need to physically travel to Alpha Centauri might be as outdated as the assumption that all computation requires human operators sitting at mechanical calculators. The future of exploration might not involve moving human bodies across space, but moving human knowledge, experience, and even consciousness. Consider what we've learned from robotic space exploration. The Hubble Space Telescope has revolutionized our understanding of the universe without any human ever leaving Earth's orbit. The Mars rovers have explored the red planet for decades, sending back thousands of images and making countless discoveries, all controlled remotely from Earth. The Voyager probes continue to send back data from interstellar space 45 years after launch. In many ways, robotic exploration has been far more successful than human exploration in terms of scientific return on investment. Advanced artificial intelligence might make robotic interstellar exploration not just feasible, but superior to human exploration. An AI probe wouldn't suffer from bone loss, muscle atrophy, or radiation sickness. It wouldn't need life support, food, water, or decades of consumable supplies. It could potentially operate for centuries, gathering data and making discoveries long after a human crew would have died of old age. And if we develop the technology for consciousness uploading, we might be able to send human minds without human bodies, experiencing the journey and exploration without the biological limitations. The search for extraterrestrial intelligence offers another perspective on our interstellar ambitions. SETI researchers have been listening for signals from advanced civilizations for over 60 years, and the silence is deafening. The Fermi paradox asks why, in a galaxy containing hundreds of billions of stars, we haven't detected any evidence of advanced civilizations. One possible answer is that interstellar travel is so difficult that even advanced civilizations don't attempt it. If true, this would mean we're not just facing engineering challenges, we're butting up against fundamental limits imposed by physics itself. Recent SETI research has expanded beyond radio signals to look for other signs of advanced civilizations, megastructures around stars, atmospheric pollution on exoplanets, even waste heat from advanced technology. The fact that we haven't found any of these signatures despite increasingly sensitive searches might indicate that technological civilizations are either extremely rare or that they don't expand beyond their home systems. Either possibility has profound implications for our own interstellar ambitions. The Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. Even optimistic versions of the equation suggest that communicating civilizations are separated by hundreds or thousands of light years. If the nearest technological civilization is 1,000 light years away, then interstellar communication becomes a multi-generational endeavor even at light speed. Interstellar travel would require timescales that span multiple civilizations. But maybe the most important insight comes from simply looking at our own technological development. Every major breakthrough in transportation, from sailing ships to steam engines to jet aircraft to rockets, has eventually hit physical limits that required entirely new approaches. Sailing ships reached the limits imposed by wind power and water resistance. Steam engines hit thermodynamic limits. Chemical rockets are bumping against the fundamental physics of reaction mass and energy density. Perhaps interstellar travel will require breakthrough physics that we haven't discovered yet, or possibly that doesn't exist at all. String theory, quantum mechanics, and general relativity hint at phenomena that might someday enable faster-than-light travel, wormholes, extra dimensions, quantum entanglement effects. But these remain firmly in the realm of speculation, and many physicists doubt whether they could ever be harnessed for practical transportation. The energy requirements for creating traversable wormholes, if they're possible at all, might dwarf even the massive energy budgets we've discussed for conventional interstellar travel. Recent discoveries in physics have been mostly confirmatory rather than revolutionary. The Higgs boson, gravitational waves, and the accelerating expansion of the universe have all validated existing theories rather than opening new technological possibilities. The standard model of particle physics, despite its incompleteness, has proven remarkably successful at predicting the behavior of matter and energy. Within this framework, faster-than-light travel appears to be fundamentally impossible, not just technologically challenging. So where does this leave us as a species? Are we destined to remain forever trapped in our solar system, looking up at the stars with longing, but never touching them? The answer might be more nuanced than a simple yes or no, and it forces us to confront some profound questions about what it means to be human in a universe this vast and unforgiving. There's something both humbling and oddly comforting about acknowledging our limitations. For most of human history, we've been explorers pushing beyond the next horizon, crossing oceans, climbing mountains, and eventually leaving Earth entirely. But the gap between stars represents a different kind of frontier, one that might be fundamentally beyond our biological reach. This doesn't diminish our achievements, it places them in cosmic context. Consider that every atom in your body was forged in the nuclear furnace of a star that lived and died billions of years ago. The iron in your blood was created in a supernova explosion so violent it briefly outshone an entire galaxy. You are quite literally made of stardust, carrying within you the history of cosmic evolution. In a very real sense, stars have already traveled to Earth. They're inside you right now, in every cell of your body. This perspective shifts the question from how do we reach the stars to how do we honor the stars that reached us? Maybe our role in the cosmic story isn't to physically travel between star systems, but to become the universe's way of understanding itself. We are matter that has become conscious, atoms that have learned to contemplate their own existence. That might be far more extraordinary than any interstellar journey. Recent discoveries in astrobiology have revealed that the ingredients for life are surprisingly common throughout the universe. The Spitzer Space Telescope and James Webb Space Telescope have detected water vapor, organic molecules, and complex chemistry in the atmospheres of exoplanets. The building blocks of life, amino acids, nucleotides, even simple sugars, have been found in meteorites and detected in interstellar space. Life might be more common than we ever imagined. If life is indeed widespread, then our inability to easily travel between stars might be part of the universe's design. Perhaps civilizations are meant to develop independently, each exploring their own unique evolutionary paths without interference from others. The vast distances between stars could be nature's way of ensuring that life has room to experiment, to evolve in countless different directions without being homogenized by contact with other civilizations. This isolation might be temporary, though. While we can't easily send humans to Alpha Centauri, we might eventually be able to send something more durable, information. As our understanding of consciousness and artificial intelligence advances, we might discover ways to transmit the essential patterns of human thought and knowledge across interstellar distances. Radio waves travel at light speed, so a signal from Earth could reach Alpha Centauri in just 4.37 years, practically instantaneous compared to a 40-year physical journey. The concept of digital consciousness transfer is moving from science fiction toward serious scientific consideration. Researchers at companies like Neuralink are developing brain-computer interfaces that could eventually allow us to upload and download thoughts, memories, and perhaps even entire personalities. If consciousness is information processing, as many cognitive scientists believe, then it might be possible to transmit consciousness as information rather than transporting biological brains. Imagine sending not spacecraft but minds to Alpha Centauri. Digital explorers that could arrive in years rather than decades investigate the system thoroughly and beam their discoveries back to Earth. These digital beings could potentially explore for centuries or millennia without aging, dying, or requiring life support. They could experience subjective time at variable speeds, slowing down during the long journey and speeding up to maximize their exploration time upon arrival. But even if we develop such technologies, there's still the fundamental question of whether we should use them. Consciousness uploading raises profound ethical questions about identity, continuity of experience, and what it means to be human. If you upload your consciousness to a computer, is the resulting digital entity still you, or is it merely a copy while the original you dies? These aren't just philosophical puzzles, they're practical questions that any civilization attempting digital interstellar travel would need to answer. The timeline for developing such technologies might be comparable to the timeline for developing practical interstellar propulsion, decades or centuries of research and development. And there's no guarantee that either approach will prove feasible. Consciousness might be more than just information processing. It might depend on specific biological substrates that can't be replicated digitally. Or the energy requirements for consciousness uploading might prove as prohibitive as those for physical interstellar travel. Meanwhile, our own solar system offers plenty of opportunities for exploration and expansion that might satisfy our cosmic wanderlust. Mars presents significant challenges, but it's vastly more accessible than Alpha Centauri. The journey takes months rather than decades, communication delays are measured in minutes rather than years, and rescue missions are at least theoretically possible. Establishing a self-sustaining colony on Mars would represent a genuine backup for human civilization and a stepping stone to the outer solar system. The moons of the outer planets might offer even more intriguing destinations. Europa, with its subsurface ocean, could harbor life that evolved completely independently from Earth. Titan, with its thick atmosphere and methane lakes, presents an environment so alien it might as well be another planet. These worlds are exotic and challenging, but they're still within our solar system, making exploration feasible with technologies we can actually envision developing. Saturn's moon Enceladus has become particularly exciting since the Cassini spacecraft detected water geysers erupting from its south pole. These geysers appear to come from a vast ocean beneath the moon's icy crust, and the water contains organic molecules and energy sources that could potentially support life. We could potentially send a probe to fly through these geysers and analyze their contents for signs of biology, all without needing to develop impossible new propulsion technologies. Recent computer simulations suggest that these local oceans might be more hospitable to life than previously thought. The tidal heating from their parent planets could maintain liquid water for billions of years, providing stable environments for life to evolve. The chemistry of these oceans, enriched by interaction with rocky cores, could provide the energy sources needed to support complex ecosystems. We might find more diversity of life in our own solar system than exists on Earth. But perhaps the most important discovery we could make is not life around other stars, but a deeper understanding of our own cosmic significance. Every advance in astronomy reveals new layers of connection between human existence and cosmic evolution. We've learned that the elements in our bodies were forged in stellar cores, that the energy powering our civilization comes from ancient sunlight, that our planet's magnetic field protects us from the same cosmic rays that make interstellar travel so dangerous. The anthropic principle suggests that the universe's physical constants are precisely tuned to allow for the existence of complex matter, and eventually consciousness. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force was slightly weaker, stars couldn't fuse hydrogen into heavier elements. If electromagnetic forces were different, atoms couldn't form stable bonds. The universe appears to be fine-tuned for our existence in ways that are either incredibly fortuitous or deeply meaningful. This fine-tuning might extend to the scale of interstellar distances. Perhaps the gaps between stars are precisely what's needed to allow for independent evolution of consciousness while preventing destructive interference between civilizations. The universe might be structured to maximize the diversity of conscious experience by keeping civilizations separated during their crucial developmental phases. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for it, might be resolved by recognizing that interstellar travel is simply too difficult for most civilizations to attempt. Rather than indicating that we're alone, the silence from space might indicate that advanced civilizations focus on developing their own star systems rather than expanding to others. This perspective suggests a different kind of cosmic destiny for humanity. Instead of becoming an interstellar civilization, we might become a solar system civilization, eventually spread throughout the hundreds of moons, asteroids, and planets in our local neighborhood. We could terraform Mars, establish floating cities in Venus's upper atmosphere, build massive rotating habitats at the Lagrange points, and develop the moons of the outer planets. Our solar system could support trillions of humans living in diverse environments, each adapted to different conditions. Such a civilization would still be connected to the stars through observation, communication, and shared consciousness of our cosmic heritage. We could build increasingly powerful telescopes to study exoplanets in detail, potentially detecting signs of life and even intelligence around nearby stars. We could send robotic probes to explore the Alpha Centauri system and other nearby star systems, accepting the decades-long journey times as simply the price of cosmic exploration. The recent success of the James Webb Space Telescope demonstrates how powerful remote sensing can be. From its position a million miles from Earth, JWST can analyze the atmospheres of exoplanets, detect the chemical signatures of potentially habitable worlds, and peer deeper into space and time than ever before. Future telescopes might be able to directly image exoplanets and even detect atmospheric biosignatures that indicate the presence of life. Radio astronomy continues to improve our ability to search for signals from advanced civilizations. The Breakthrough Listen project monitors millions of stars for artificial signals using algorithms sophisticated enough to detect even weak or unusual transmissions. If there are other technological civilizations within a few hundred light years, we might eventually detect their presence through their electromagnetic emissions, intentional or otherwise. Think about what we've actually accomplished in just a few centuries of scientific development. We've gone from believing the Earth was the center of the universe to understanding our place in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. We've learned that we're made of elements forged in the nuclear fires of ancient stars, that our DNA connects us to every living thing that has ever existed on Earth, that our planet is a tiny oasis of complexity in a vast cosmos that took 13.8 billion years to create us. The very fact that we can stand here on this small rocky world and contemplate the distance to Alpha Centauri is itself a miracle that required the entire history of the universe to unfold exactly as it did. Every atom in your body has traveled for billions of years to be part of you in this moment. You are not separate from the cosmos. You are the cosmos becoming aware of itself, matter organized into a pattern complex enough to contemplate its own existence. If you made this far, I am sure you will love this other video at the left side of the screen. What if we could travel 1 light year per second across the cosmos? In this mind-blowing thought experiment, journey across the cosmos at impossible speeds and witness the universe transform before your eyes. See you there.